Hello students, welcome back. We completed section 4 along with a brief review on lesson 2. Now let's go to section 5, the least common multiple. I hope everybody remembers the definition. Given pair of integers a and b, not both of them are 0, then the largest integer that divides both a and b always exists uniquely. We call it the greatest common divisor. And we also prove that it satisfies the linear combination property, Bezout's theorem. That was GCD. Now how about the LCM? Let's begin with a pair of integers a and b, but this time both are non-zero integers. Then the smallest positive integer that's divisible by both a and b always exists uniquely. Yes, we proved that. We proved that in the previous lesson, in lesson 3. We call it the least common multiple, and we denote it LCM of a and b like this, or simply a comma b like that with bracket when there's no danger of confusion. And in trivial cases, when either a or b is 0, then the LCM is defined to be 0, but let's not worry about these kind of really special cases. So that's the LCM, and here are some properties of LCM. But come on, these are too trivial, so I'll leave all those properties to you as exercises. Maybe homework, maybe not even worthy of that. Commutativity, come on, that's too simple. This one requires some work, but tedious, too tedious, so let's not worry about any of those. Let's just accept all those. And as for homework problems, maybe I will assign all these, or maybe some of those. I'll do something about those. In any case, I'm not going to waste any class time on these. Simple but too tedious. Instead, let's focus upon the kind of properties that are worthy of some class time. And let's begin with a property on GCD. Remember this property? We went through this already. C divides A and C divides B, then C divides the GCD. Remember the proof? We went through that already, so I didn't do it here. Basically, the GCD is then D is some linear combination. Therefore, C divides A, so this A, which I'm highlighting in blue, is C times some integer. And then this B, which I'm highlighting green, is some, again, a C times some integer. So C is common, I can take it out, and what's left is some integer, Rx plus Sy, which is an integer, so C divides D. That's the proof actually. This is whole proof. We have a counterpart here for LCM. If C is a common multiple, in other words, it's divisible by both A and B, then it is divisible by the LCM. Now, how do you prove that? That takes a bit of an effort. Let's see if we have positive common multiple of A and B. Let's begin that first, and the negative case is left to the students. As a matter of fact, that's really nothing. And C is negative, then C is negative of, say, C prime, which is positive, and work out for C prime, and then put negative sign at the very end. So we don't really have to worry about negative case. So that part is left to the students. Now C is a positive common multiple of A and B, and then M is the least common multiple. And what we want to do is to apply the division algorithm, get the remainder, and we're going to prove that remainder is 0. Make sense? One way to prove that something is divisible by another number is to prove the remainder is 0 after the division algorithm. That's basically what we are going to do. So upon division algorithm, C is some quotient Qm plus R, and R is greater than or equal to 0 and strictly less than M. And then, does it ring a bell strictly less than M? It should already ring a bell to you, because M is defined as the least common multiple. So something is less than M. Already there is a kind of setup for proof by contradiction. Okay, alright, let's go to the next step. Both C and M are common multiples of A and B. So A divides C and A divides M. So flip this over to the other side, then what you get, R is C minus Qm, which is A divides this, so some number XA, and then Q, and then some number times A, YA. So this is an integer times A form. Let's make it a little bit smaller. And that way we can prove that R is divisible by A. Make sense? And if I do the same thing, very same thing, with respect to B, so instead of X, X prime B, and then instead of Y, Y prime and then B, so that we have integer times B, yes, R is divisible by B as well. Or you can use mod operation. Congruence modulo M. Excuse me, did I say modulo M? Sorry. Congruence modulo A, and then congruence modulo B. You see, M is divisible by A, so as far as A is concerned, it's 0. Same for C, divisible by A, so it's 0. So R is equal to 0 modulo M, or R is divisible by, I keep saying modulo M, excuse me. R is divisible by both A and B, so R is a common divisor, okay, common divisor, and strictly less than M, which is the least common multiple. Oh, I said it wrong again, excuse me. Let me open this again. I said common divisor, I should have said common multiple. R is a common multiple of A and B. You see, it's divisible by A and it's divisible by B. So R is a common multiple of both A and B, and then less than the least common multiple. Therefore, R should be 0. If R is not 0, then there's a contradiction. You get a common multiple that is less than the least common multiple. All right? So R has to be 0. So R is 0, and therefore M divides C, and isn't that what we wanted all along? We wanted to prove the LCM divides C. In order to prove that, we devised this division algorithm format, and we wanted to prove R equal to 0, and that's basically what we did. And please forgive me of misspeaking several times about divisor versus multiple and mod A versus mod M. Sorry about that. What's written here is correct. R is congruent to 0 modulo A. In other words, R is divisible by A. R is a multiple of A. Same for B, congruent to 0 modulo B. So R is a multiple of B. So R is a common multiple of A and B, but strictly less than the least common multiple. It has to be 0. And that's what we want you to prove. We got it. So LCM divides any positive common multiple. As for negative, the detail is left to the students. All you have to do is multiply negative 1 at the very end of the proof. Okay, one more, and we have enough time for this. Okay, all right, let's try that. The product of a pair of non-zero integers is equal to the product of the GCM and LCM, the product property. The proof actually much simpler than the previous proof. Let D be the GCD and M as AB over D, and we're going to prove that this M is the least common multiple. First, this is an integer, right? B over D is an integer. Do I have a little bit bigger version? Yeah, okay, all right. B over D is an integer because D divides B. So this is A times integer. So A divides this M. On the other hand, D divides A, so A over D is an integer. So this is an integer times B, so B divides M. Oh, what do we have? M is a common multiple. Common multiple of A and B. Now, is it the least common multiple? Well, we can use a previous property. Let C be any positive common multiple. Then A divides C, and oh, excuse me, there's a typo. Common multiple, B divides C. Then C over A is an integer, yeah, A divides C. C over B is an integer, okay, so common multiple, all right. C over A and C over B are both integers. And then look at this. We apply some interesting algebraic manipulation. C over M is, by definition, maybe a little bigger font is going to be helpful here. C over M, but M is AB over D, so this one is C over M, which is AB over D. So flip it over, CD over AB, all right, so far so good. And what is this D? AX plus BY form, because this Bezout's theorem. And then if we apply this simplification, A and A cancel out, C over BX, and B cancel out, C over AY. Hey, what do we have? We have a linear combination again. So C over M is a GCD. So M divides C, and then M divides C, and they are both positive. Therefore, M is smaller of the two. That concludes a proof that M is indeed the LCM. Okay, all right. It was a bit harder than I originally expected, but that's how the proof goes, using Bezout's linear combination property along the way.